In the last lecture, we were looking at forced convection past a flat plate. Okay. So this was the surface x, z. You have a heated section for x greater than 0. Okay. Velocity profile had a no slip condition at the surface. Velocity profile had a no slip condition at the surface. In the limit where convection is strong, you would expect the disturbance due to the temperature field to be restricted to a thin region close to the surface. Okay. The disturbance due to the temperature field is restricted to a thin region close to the surface of thickness delta. Okay. Within this region, we approximate. Okay, within this region, we approximate the velocity profile as a linear velocity profile. Vx is equal to Vs prime z. Okay. Equation, okay, we include cross stream diffusion and streamwise convection. Okay. Cross stream diffusion and streamwise convection are included, okay, in the balance, okay, within this boundary layer. Okay. Similarity variable eta is equal to z by delta of x. Okay. Original equation Vs prime z, okay, partial t star by partial x is equal to alpha times partial square t star by partial z square. Okay. And the boundary conditions. Okay. So, the wall temperature here is Tw, T infinity far from the surface, and T infinity before the start of the heating section. Okay. Okay, those are the configurations. Okay. Define the temperature T star is equal to T minus T infinity by Tw minus T infinity, okay, which means that at the heated surface T star is equal, okay, here T star is equal to 0, T star is equal to 0 before the start of the heated section, and T star is equal to 1, okay, in this heated section. Okay. So, the boundary conditions are T star is equal to 1 at z is equal to 0 for x greater than 0, T star is equal to 0 for z going to infinity, and T star is equal to 0 at x is equal to 0 for z greater than 0. Okay. We had substituted in terms of the similarity variable, okay, and if you recall, we had got an equation of the form okay, Vs prime, okay, delta square d theta by dx, Vs prime by alpha, okay, into minus eta dt star by d eta is equal to d square t star by d eta square. Okay. And we had set this equal to a constant C delta in order to get a similarity solution. Okay. Turns out that you can set C delta to any value, okay, it does not matter. I showed you that the temperature field in terms of the similarity variable eta does depend upon C delta. In terms of the original variables x and z, this will not depend upon eta. Okay. Therefore, you can set C delta to any value that you want. Simplest is to set C delta equal to 1, in which case the temperature field is of the form 1 minus integral 0 to eta d eta prime e power minus eta prime cubed by 3 by integral 0 to infinity d eta prime minus eta prime cubed by 3. Okay. Okay. So, that is the equation for the temperature field. Okay. The heat flux at the surface k times partial t, okay, is equal to minus k into t w minus t infinity by delta. Okay. Into 3 power 2/3 by gamma of 1/3. Okay, where the boundary layer thickness delta, okay, delta is equal to 3 alpha x by Vs prime whole power 1/3. Okay. I set C delta to 1 in this case. As I said, it does not matter what C delta is, the result you get in terms of x and z turns out to be the same. Okay. Therefore, this is equal to k into t w minus t infinity divided by 3 alpha x by Vs prime whole power 1/3, 3 power 2/3 by gamma of 1/3. Okay. So, that is the heat flux at a location x. What is the average heat flux? Okay. What is the average heat flux? Q average is equal to 1 over the total length integral 0 to L, okay, dx of qz at z, okay, equal to 0, okay, which is a function of x through the dependence of x power minus 1/3 here, okay, through the dependence of x power minus 1/3 over here. Okay. So, everything in this equation is a constant except that 1 over x power 1/3. Okay. So, I will get k into t w minus t infinity, okay, divided by 3 alpha by Vs prime power 1/3, okay, into 3 power 2 by 3 by gamma of 1/3, okay, into 1 over L integral 0 to L dx into 1 over x power 1/3. That integral is 3 times x power 2/3. So, you get an L power 2 by 3 times 3. Okay. And the final expression you will get for Q average is equal to k into t w minus t infinity, okay, into 3 power 4 by 3 divided by alpha L by Vs prime whole power 1/3, okay, into 2 gamma of 1/3. Okay. Because integral of x power minus 1/3 is x power is 3 by 2 x power 2/3, okay, and there is a 3 power 1/3 in the denominator, 3 power 2/3 in the numerator here multiplied by 3. Okay. And you can evaluate these constants. It is approximately equal to 0.81 k into t w minus t infinity divided by alpha L by Vs prime whole power 1/3. The Nusselt number is equal to Q average by k into t w minus t infinity by L. Okay. The Nusselt number is Q average by k into t w minus t infinity by L, which is equal to 0.81, okay, into Vs prime L square by alpha whole power 1/3. Okay. You can see you have a Vs prime power minus 1/3 in the denominator here and alpha power 1/3 in the denominator. Okay. And that factor of L will go to the numerator and you will get an L square by alpha. Okay. So, this is equal to equal to 0.81 into the Peclet number power 1/3, where the Peclet number is not based upon the velocity, but rather the velocity gradient and the total length. Okay. It is not based upon the velocity, but it is based upon the velocity gradient and the total length. Okay. So, that is how you use a similarity variable, similarity solution to get the Nusselt number correlation for the flow past a flat plate, okay, for the Nusselt number correlation for the flow past a flat plate. Okay. Okay. So, in the flow past a flat plate, there was no length scale in the z direction. The only length scale was the length scale along the flow direction. Okay. The only length scale was the length scale along the flow direction. Okay. This, however, this can also be used when there is a length scale in the z direction, provided that height in the z direction is much smaller than the boundary layer thickness. Okay. You can also use it in cases where the height is much smaller than the boundary layer thickness. Okay. So, one example is for the heat transfer in a pipe. Okay. Okay. In that case, okay, so let us say that this is the radial coordinate r. Okay. The pipe diameter is d, okay, and the radius of the pipe is r, and I have a parabolic flow in a pipe. I have a parabolic velocity profile in a pipe. Okay. My x coordinate is calculated from the start of the heating section. Okay. So, let us say the pipe is the start of the heating section is at x is equal to 0. Okay. In that case, the effect of at high Peclet number, the effect of the heated surface will diffuse into the flow up to a length scale delta. Okay. It will diffuse into the flow up to a length scale delta. Okay. Provided that the length scale delta is much smaller than the radius of the pipe, I can still assume that it is diffusion into an infinite medium. Okay, I can still assume that it is diffusion into an infinite medium and use the same calculation for the temperature profile and the heat flux that I had for the diffusion into an infinite medium. Okay. Only thing is that I have to take into account the velocity gradient at the wall of the pipe while I am calculating my Nusselt number correlation. Okay. For a parabolic flow, okay, for a parabolic velocity profile, the velocity Vx, okay, for the Hagen-Poiseuille flow in a pipe is equal to 2 times V average into 1 minus r square by r square, okay, which is equal to 2 V average into 1 minus r is equal to d by 2. So, I will get 4 r square by d square. Okay. Which means that the velocity gradient at the wall, okay, Vs prime is equal to dVs by dx at r is equal to r. Okay. If you take the derivative of this with respect to r, you will get minus 8 V average r by d square at r is equal to d by 2. Sorry, it should be 16 here, because when I take the derivative I get 2 times 4 times r square. So, this is minus 16. Okay. And since r is equal to d by 2, this just becomes equal to minus 8 V average by d. Okay. So, that is the strain rate at the wall. Okay. So, that is the strain rate at the wall of the pipe. Okay. Okay. So, therefore, this is dVx S by dx, okay, the strain rate at the wall of the pipe. If I calculate it going into the pipe, note that my z coordinate was in the direction opposite to the r coordinate, okay, and the strain rate was calculated with respect to the z coordinate, which was calculated from the wall, okay, not from the center. Okay. So, therefore, the Vs prime, so the slope Vs prime is equal to 8 V average by d. Now, the average flux, okay, Q average, we had calculated it as 0.81 K into Tw minus T infinity. Tw is the wall temperature and T infinity is the temperature, okay, in the fluid, okay, into alpha L by Vs prime power 1/3. Okay. And I have to substitute this for Vs prime. Okay. I have to substitute this for Vs prime. Okay. This is equal to 0.81 K into Tw minus T infinity divided by alpha dL by 8 V average whole power 1/3. Okay. The Nusselt number, okay. Nusselt number for a pipe flow is defined with respect to the pipe diameter. Okay. The Nusselt number for a pipe flow is defined with respect to the pipe diameter. Okay. Q average by K into Tw minus T infinity by d. Okay. The Nusselt number is defined with respect to the pipe diameter, okay, for flow in a pipe. Okay. And you can easily see this factor of 8 power 1/3 is just 2. Okay. 8 power 1/3 is just 2. So, I will get 1.62, okay, into V average d square by alpha L, okay, whole power 1/3. Okay. This d in the denominator, you can take it into the numerator. Okay. Okay. And I will get a d power 2/3 because this d cancels out with this d power 1/3 in the denominator to give me a d power 2/3. Okay. This is equal to 1.62 V average d by alpha power 1/3 into d by L power 1/3. Okay. Which is equal to 1.62 Pe power 1/3 times d by L power 1/3. If you recall, the Peclet number Pe, okay, is equal to V average d by alpha, which can also be written as V average d by nu into nu by alpha. Okay. V average d by nu is rho V average d by mu, which is the Reynolds number, and nu by alpha is the Prandtl number. Okay. So, therefore, I get the correlation, this is equal to 1.62 R e power 1/3 P r power 1/3 into d by L power 1/3. Okay. The standard correlation is used is slightly different. Okay. The prefactor used is 1.86. Okay. That is the standard correlation that is used for pipe flow. Okay. However, to within this constant, okay, to within this constant, we managed to get the correlation for the heat transfer in a pipe flow using just a similarity solution. Okay. In the high Peclet number limit, we postulated that the boundary layer thickness is small, okay, compared to the length of the domain. Based upon that, we got a similarity solution. Okay. We define eta as z by delta of x, substituted that into the equation, found the condition under which the equation is independent of x and z and depends only upon eta, okay, the similarity variable, and the boundary condition also depends only upon eta, the similarity variable. Okay. And using that, we had calculated the temperature field in terms of eta and the boundary layer thickness delta as a function of x. Using that, we had calculated the local heat flux and the average heat flux. That average heat flux was substituted into the Nusselt number correlation to get a correlation for the was substituted the average heat flux was substituted into the definition of the Nusselt number to get a correlation for the Nusselt number. Okay. And using that, we got the correlation for the heat transfer in a heated flat plate as well as heat transfer in a pipe. The only remaining thing is the condition here. Okay. Recall the condition that delta has to be much smaller than r. Okay. Delta has to be much smaller than r, which means that delta by d by 2 has to be much smaller than 1. Okay. Delta is given by 3 alpha L by the Vs prime, and Vs prime was 8 V average by d whole power 1/3. Okay. Divided by d by 2, okay, has to be much less than 1. Okay. And you can do some simplifications here, okay, and what you will find if I take the cube of this. Okay. So, if I take the cube of this, this is also much smaller than 1. So, 3 alpha L by, okay, three alpha L d by 8 V average into 8 by d cubed has to be much smaller than 1. Okay. And I get the final condition that L by d is much smaller than V average into d by alpha, okay, whole to, okay, and 3 here. Okay, V average d by 3 alpha, okay, which has to be much less than Peclet number by 3. Okay. Okay. So, the condition that this boundary layer thickness, okay, that the boundary layer thickness has got to be much smaller than the radius of the pipe, okay, than the radius of the pipe for the boundary layer approximation to be valid. Okay. The boundary approximation is valid only when the boundary layer thickness is much smaller than the radius of the pipe. That means that the length by diameter ratio has to be much smaller than PE by 3, the Peclet number by 3. Okay. The Peclet number is V average d by alpha, okay, so, or d by the diffusion coefficient. Okay. So, therefore, you require that the Peclet number, the length by diameter, so you require that the Peclet number has to be large. Okay. The Peclet number has to be large for this analysis to be valid. That is, the Reynolds number times the Prandtl number has to be large, and L by d has to be much smaller than P power the Peclet number in order for the boundary layer analysis to be valid. Okay. In many cases, it is not large, and that is the reason that the actual correlation does not correspond to the one that we have just calculated. Okay. So, this shows how we can apply the boundary layer analysis for the flow past a flat plate to the flow in a pipe. Okay. Next lecture, I will talk about the boundary layer analysis for a stagnation point flow. Okay. So, typically if you have a spherical particle, for example, and you have flow towards that spherical particle going around, okay, and Over here you have a decelerating velocity and then you have velocity that accelerates upstream and then decelerates downstream of this. And if you look very close to the surface, okay, you will find a flow that looks something like this. Okay. You have a separation with velocity going on one side and on the other side. Okay. That is called a stagnation point flow. To write it slightly differently, okay, to draw it slightly differently, okay, if this is x and this is the z coordinate, the velocity comes like this. Okay. And if we have temperature T is equal to T infinity far from the surface and T is equal to Tw on the surface, a heated section of length L, okay, how can we calculate the heat flux, the temperature field, the heat flux using a similarity transform where the velocities are approximately given by Vx is equal to some constant x times z and Vz is equal to minus half k z square. Okay, that is the approximation for the velocity close to the surface. Okay, that is the approximation for the velocity close to the surface. Okay. The equation for the temperature field, okay, I will once again define temperature field is equal to T minus T infinity by Tw minus T infinity. Okay, that is a scale temperature. That means at the surface T star is equal to 1, okay, far from the surface T star is equal to 0. Okay. Okay. The equation for the temperature field becomes, okay, Vx partial T star by partial x plus Vz partial T star by partial z is equal to alpha partial square T star by partial z square, neglecting the streamwise diffusion in comparison to the cross stream diffusion and assuming that the boundary layer thickness within which there is a disturbance to the temperature is much smaller than the length of the plate L. Okay. So, this problem of heat transfer at a stagnation point flow, how do we calculate the temperature field in terms of the similarity variable and the boundary layer thickness in terms of the downstream distance? Okay. How do we calculate those two? That I will continue in the next lecture. I will see you then.